preparation of supported niobium oxide catalyst. The authors are Jheng and Israel Wax of Lehigh University. The paper will be presented by Mr. Jheng.
Today my talk, the title is niobium oxide, a new precursor for the preparation of supporting niobium oxide catalyst. First, I would like to introduce my advisor, Dr. Israel Wax. He cannot attend this presentation because his father died 2 weeks ago. I will give him best regard. The objective of our study is to develop an aqueous preparation of supporting niobium oxide catalyst. In the past, the niobium pentachloride and niobium hydroxide has been used for non-aqueous preparation of supporting niobium oxide catalyst. This precursor is very sensitive to air, so we need a special environment to do the preparation. Because once the precursor contact with air, you start to decompose the MD2O5 crystallite. The molybdenum oxalate and the niobium oxalate and the vanadium oxalate has been proven successfully for aqueous preparation of supporting molybdenum oxide and the vanadium oxide. So we choose a niobium oxalate for the preparation of supporting niobium oxide catalyst. We're using Raman spectroscopy to study solution chemistry of niobium oxalate with respect to solubility and the pH. We also study the coverage effect and the calcinating temperature effect on supporting niobium oxide on aluminum by using Raman spectroscopy. Normally, niobium oxalate doesn't dissolve in water. From this solubility of niobium oxalate versus wave fraction of oxalic acid diagram, we can see the solubility of niobium oxalate in water can be dramatically increased by adding oxalic acid into solution. When there's no oxalic acid added, the solubility of niobium oxalate is around 0. And we add a little bit oxalic acid, then the solubility increases dramatically. And add more oxalic acid, the level starts to go. Sorry? The curve starts to level off. Up to a certain point, add more oxalic acid, the solubility starts to decrease. We use Raman spectroscopy to characterize the niobium oxide compounds. Basically, Raman spectra is divided into 3 regions. In the high wave number region from 800 to 1200 is characterized to niobium oxygen terminal double bond stretch. In the region between 400 and 800 is characterized to niobium oxygen single bond and niobium oxygen niobium linkage symmetric stretch. There's an associated bending mode in the low wave number region. This is the well-known structure of the MB619. We can see there's a 6-terminal niobium oxygen double bond, which Raman band appear around 870. They also have many of the niobium oxygen niobium bonds, which in Raman band appear 530. And there's associated bending mode in the low wave number region. Another common niobium oxide compound with a Mb205 crystallite, which is the structure shown. There's no double bond in the high wave number region. There's only a broad and strong bond, and the band appear at 690 is due to the MbO6 octahedral structure. As for our study material, niobium oxide, there's a strong band at 950. So we know there's a terminal niobium oxide terminal double bond in the structure. Also, there's a peak appear around 570. It's due to the once the oscillator chelate to the niobium, it like to form a bidentate structure. So it's due to the symmetric of this bidentate structure. They also have a bending mode in the low wave number region. And we use Raman spectroscopy to study the solution chemistry of niobium oxide. We vary the pH from 0.5 to 5 by adding ammonium hydroxide. The Raman spectra shown, there's two bands in the high wave number region. And the intensity of these two bands is changing with the increasing pH. According to equilibria, we assign the band at 930 is a 3 oscillate chelate to the niobium metal. The low wave number region at 910 is assigned to 2 oscillate chelate to the niobium metal. Also, this niobium oscillate bidentate structure appear around 570. But at the pH 5, there's additional band was absorbed around 680. It's consistent with Mb205 crystallite. So we know at a high pH, the niobium oxide start to decompose to Mb205. To summarize the solution chemistry of niobium oxide, we know there's two kinds of niobium oxide species in the solution: 3 oxide group and 2 oxide group. They reach equilibrium. Once we add ammonium hydroxide, the 3 oxide group, the 1 oxide group will be replaced by the hydroxide ion. So we know the intensity of the 930 band decreased, the intensity of the 910 band increased. Further add hydroxide to the solution. We increase the pH, and this is start to form the Mb205 crystallite. So we know the solubility and the stability of the niobium oxide in solution. Now we start to prepare the supporting niobium oxide catalyst. We're using the incipient wetness impregnation method to prepare supporting niobium oxide catalyst. The outside support, we're using gamma aluminum from Harshar surface area 250 meters square per gram. And the procedure we're using is we impregnate the niobium oxide on aluminum and dry at room temperature 16 hours, and further dry at 120 degrees to remove the water. Then calcine at a temperature between 500 and 950 to remove the organic ligand to form the supporting niobium oxide on aluminum. But we don't know what kind of structure of niobium on aluminum, so we also study by Raman spectroscopy. Showing here is a series of Raman spectrum. Its coverage changing from 1% to 25%. We can see a low loading. There's a band appear around 900. It's due to the terminal niobium oxide double bond. We increase the loading to 15%. The surface niobium oxide start to form the niobium oxide niobium linkage. So this band is due to the symmetry of the niobium oxide niobium linkage. When we further increase the loading, we can increase the intensity of this band. So for the Raman suggests there's two kinds of surface niobium oxide present on the aluminum support. We also do some X-ray diffraction data. X-ray derivative data shown when there's a high loading of niobium or aluminum, around 25%, we saw the very weak niobium phases start to appear. We further increase the loading, the intensity of the Nb2O5 phases increased. By the low loading, they only see the aluminum phase, strong aluminum phase. There's no Nb2O5 showing. So from the Raman data and the X-ray reflection data suggest the niobium, supporting niobium oxide from aluminum approach monolayer around 22%. It is consistent with the well-known molybdenum, supporting molybdenum oxide from aluminum. We know there's two kinds of surface niobium oxide on aluminum. Next we're going to study the calcinating temperature effect, the surface niobium oxide species. With a 5% niobium on aluminum, it's a calcine the temperature between 500 and 950. We can see the surface niobium band didn't change, and there's no indication of forming the Nb2O5 crystal band, which Nb2O5 crystallite, which band appear around 690, or aluminum niobate compound, which major band appear around 930. There's an additional band appear around at the low wave number region. That's due to the phase transformation of gamma aluminum to the theta and theta aluminum. So from the Raman spectrum suggests the surface niobium oxide species on aluminum support stable to elevated calcination temperature. In conclusion, we know the aqueous preparation of supporting niobium oxide catalyst was achieved, and the solubility of niobium oxalate in aqueous solution can be dramatically enhanced by adding oxalic acid. And when we dissolve the niobium oxalate into aqueous solution, there's two kinds of niobium oxalate species exist, and the relative concentration of the niobium oxalate species in solution depends on the pH of the solution and the oxalic acid concentration. Also, there's two surface niobium oxide species present on aluminum support, and the relative concentration of the surface niobium species depends on niobium oxide coverage. Finally, we know surface niobium oxide species remain stable at a high temperature calcination. Finally, I would like to thank the niobium product company for their financial support.
Thank you very much. The paper is now open to questions. Okay, if not, then thank you very much. Okay, after a long journey, I guess we are finally getting into the final paper, which is a contribution from University of Iowa entitled Development and Design of Supported Molten Salt Catalyst.